Now, today we're going to start one of the most popular distributions, the normal distribution. But since we're getting closer to Halloween, I thought I'd show you the paranormal distribution. We won't be spending much time on that one today. All right, so first of all, let's go ahead and talk about density curves. And we're going to start with this example. Zoe frequently takes the Line 4 subway in New York, and this train comes every 20 minutes. What is the least amount of time she could wait? And let's just assume a normal schedule and it's going every 20 minutes. Well, the least amount of time she could wait is she gets there just as the train's arriving and she waits 0 minutes. What's the most amount of time she would wait? Well, if the train just left, the doors closed, she'd have to wait another 20 minutes. Is one wait time more likely than another wait time? No, unless, there's some sort of lineup on the schedule. We're going to assume that she's just like randomly coming in. So all the wait times are equally likely. In that case, what do you think is the probability that she will wait 5 minutes or less? Well, that would be 5. If you thought of a timeline of from 0 to 20, 5 is only 1/4 of that time, or 25%. How about that she waits between 3 and 4 minutes? Well, that's only 1 minute in the 20-minute time frame, so that would be 5% that she waits between 3 and 4 minutes. Same thing if we have her ask the probability she should wait between 4 and 5 minutes. It should be the same. Now I'm going to go ahead and create a graph of the probabilities, and I know I need to cover from 0 to 20, and I'm going to show you that I also need to cover from 0 to 0.05 on the height. Why is that? Well, we said the probability that 3 to 4 minutes would be 0.05. So in this area, if it falls anywhere in here, that's 5% of the time. Same thing for 4 to 5. There's no reason to think any of the other heights would be different. And so if I fill in the probability of 5 minutes or less, that would be adding 3 bars here, or the total area would be 0.25, 5 bars of 0.05. And then if I look at distribute the whole thing, then I am going to go from 0 to 20 minutes. And that area, well, I'm going to have 20 bars of 0.05. That area is 1. And that makes sense because 100% of data values must fall between 0 and 20 minutes. So this visual representation we call a density curve. And it's always on or above the horizontal axis. Why is that? Probabilities can't be negative. And the area, when we add up the whole thing, is 1. For those of you doing calculus, you may have done areas under the curve, and there's some very cool distributions you can integrate actually and find the area, but they're not necessarily easy integrations. All right, so now they do come in a variety of shapes. This one right here is uniform since probabilities are roughly the same. And they're frequently used when we use uniform distributions for random number generators, programs, video games, when we want things to be spread equally between certain values. Now, there are also other types of density curves. I created these using Shodor, which is a great resource. And let's go ahead and show you what these mean. So we're going to start with this skewed left distribution, which we've already sort of talked about. Here's your mean, there's your median. And these red lines are 1 standard deviation below and 1 standard deviation above the mean. So you can see they're equidistant from the mean. And here, since the mean is less than the median, we are skewed left. This one is a single-peaked unimodal, roughly symmetric, actually really symmetric. And there's your mean. And guess what? Your median's in the same spot. And there's your mean minus and your mean plus the standard deviation. Your mean and median are the same. Then a skewed right distribution would have your mean to the right of your median, and there are the standard deviations again. And this is going to come in handy here in just a second. So you're going to see why I'm curious about things that are 1 standard deviation away. Again, because this is skewed right, the mean is greater than the median. Now, the mean is a cool point because if you actually were trying to balance these curves, if you tried to pick a point to balance it, you would put it under the mean. All right, so that's where the curve balances if I were to cut it out and try to balance it. The median cuts the areas in half. All right, so you have half the data points before and half the data points after. Now, what type of distribution would work for the height of an average person or SAT scores? Here you can see these are actually, they're not uniform, so we can't use that. They tend to be bell-shaped. And so I'm going to take a look at flipping a coin over many times to introduce you to a very popular distribution. This is a virtual simulation for flipping a coin. So here it shows one flip and the probability distribution for the number of heads. So for one flip, you would guess you'd either get heads, you get 0 heads half the time and 1 head half the time. If I go to 2 flips, then you get 0 heads a quarter of the time. You can see it here. 1 head half the time, 2 heads a quarter of the time. And as I keep increasing it, you can see the number of heads changes based on the number of combinations we can get. And the shape is starting to get a little familiar. In fact, as I keep going up and up and up, what does this look similar to? This looks a lot like the normal distribution. And in fact, when you're doing a binomial distribution, and this is only with 50 flips, it already is looking very much like a normal distribution. Even if I were to bring it down to, say, 25 flips, it would still look very similar to normal distribution right there. Okay, so a normal distribution is symmetric, single-peaked, and bell-shaped. Any normal distribution can be specified by just 2 numbers, the mean, mu, and the standard deviation, sigma. Now, we have a nice empirical rule because we know the shape of these distributions so well. It's called the 68, 95, 99.7 rule. And that is that 68% of the data is within 1 standard deviation of the mean. So if I do this, these marks represent standard deviations. 68% of my data is right here in the yellow. Then that means I would have 34% between the mean and 1 standard deviation below, and 34% between the mean and 1 standard deviation above. 95% of the data is within 2 standard deviations of the mean. So that would be going from here all the way to here. And that would add the green areas to the yellow. How did I get the 13.5? I said, well, okay, this total area is 95. Subtract the 68, and that gives me 27. Divide it in half for each side, and I get 13.5. You don't have to memorize these numbers, but they're kind of handy for what we're going to be doing with the empirical model. And later, you're just going to be using z-scores. So again, you do need to memorize these 3 rules, the 68, 95, and 99.7, which is 3 standard deviations from the mean. But you don't need to memorize these individual percentages between each standard deviation value. Now, I do have the 0.15 here. Why is that? Well, if I have 99.7% is between 3 sigma below and 3 sigma above, that leaves 0.3% unaccounted for, which would be the value on the left and the value on the right. I'm going to go ahead and leave these pieces for right now because it'll just make it really easy to look at some of the examples we have. So in this first example, a 1903 study on inheritance, the average height of mothers was 62.5 inches with a standard deviation of 2.4 inches. So the normal model is 62.5 and 2.4. You can draw the model by putting 62.5 there and then going 2.4 away every time. All right. What percentage of people are less than 62.5 inches tall? Well, I really don't have to do any math. It's half the curve. It's 50% or less than the average. Now, if I added these up, I would also get half. Then the question is, what is a percentile of heights at 67.3 inches? So that would be right here. Well, that percentile is all the percentages below that value. So I need to add the 0.15, the 2.35, 13.5, 34, 34, and 13.5. Oh, and I get 97.5%. So 67.3 inches is in the 97.5th percentile using a normal model. Let's go ahead and look at a study investigating the effect of car speed on accident severity. So they recorded vehicle speed on 5,000 fatal accidents. The mean was 42. Standard deviation is 12. So we're going to go ahead and set up our model. 42 is the mean, and then I'm going to go 12 away in each direction. until I go 3 standard deviations away. All right. What was the interval of vehicle speeds for 68% of the data? You should have memorized that that's 1 standard deviation from the mean. So it's just from 30 to 54 miles per hour. All right. So from here to there. What was the interval of vehicle speeds for 95% of the data centered about the mean? So now we're going to go 2 standard deviations away in each direction. We're going to go to 18 to 66. So that's the interval. Finally, 3 standard deviations from the mean is 99.7%. And so you would say from 6 miles per hour to 78 miles per hour. Again, you don't need to memorize these little slices. You might want to draw the curve because I think it kind of helps to see the shape and the breakdown. But most of our work is going to be, we'll do some empirical rule, but most of our work is going to be other numbers that are in between. So speaking of which, what if I have a z-score, and we're talking about z-scores here, of 1.82, because z's tell us how many standard deviations away things are. Well, there's a table of z-scores, and they give the percentile for different z-scores. So what I can do, first of all, I'm going to mark 1.8 on my graph. So before I even look at the table, using common sense, is this going to be more or less than half? Well, because I've already got half the curve shaded plus more, a good chunk more, it's more than half. Do I think it's more than 80%? Well, using my empirical, if I were to like label all these pieces and put them in, I'm going to go, yeah, that looks like that's more than 80%. In fact, I get 84% just from these pieces. Now we're going to use the table at right to get a much more exact value. So what we do, this table shows z-scores, and there are 2 sides typically to the table. You'll have negative z-scores when it's below the mean, and positive z-scores when it's above the mean. And if I want a z-score of 1.82, so I come to this, I go down this column until I get to the row with 1.8. This is 1.80, 1.81, 1.82. See how that shows the hundredths place right there. So using that table, the percentile is 96.56 percentile. So this makes sense based on our graph. There's your 1.8. All right, so again, we're going to go ahead and look at Tiger Woods drives, and we assume there's a mean of 304 and a standard deviation of 8, and that it's approximately normal, so we can use a normal model. What is the percentile for a drive at 286 yards? Well, first we're going to find the z-score, which is a standardized score, so I can use this table. And if I go value minus the mean and figure out the standard deviations, 286 minus 304 is negative 2.25. So it's somewhere roughly around here, and this shaded area to the left. Well, this table is designed to give me the percentile, so that's kind of nice. Negative 2.25 is up here on this row, and then negative 2.2 is here, and to get the 5, I want this column, and so my value is 0.0122. So that means it's at 0.0122 or 1.22th percentile. Using the normal model for Tiger Woods drives, a drive of 286 yards would be in the 1.22th percentile, or you could say roughly the 1th percentile. So that would be very low for Tiger Woods. All right, so when we do use the tables, they only do the less than probabilities, not the more or in between probabilities. So we're just going to practice with some standardized scores here. What percent has a z-score above 0.21? So here I'm asking above. So I wanted above this value, roughly 0.21, and that means it's kind of this green area here. Now if I go to the table, 0.21 is 5.832, but that 5.832 is not the green area, it's the yellow area here on the left. So if I want to find the green area, I know the total is 1. So I can go 1 minus 0.5832 and get 0.4168. That means 41.68% of z-scores are at 0.21 and above because I'm looking at the above. Below is pretty easy. It's just that number, 58.32%. Now, what if I wanted between 0.21 and 1.82? I'm going to use this graph here to do that. So there's 1.82 from before. And remember, that was the area that was the 0.9656. Then we have 0.21 right there, and that's this area, the yellow area above. So I have 0.9656 for the whole blue area, 0.5832 for the yellow, but I'm kind of looking for this reddish purple area. It's really red. So blue plus the yellow, blue is the yellow plus the red. So when I put the yellow and the red together, I get the blue areas. I'm going to go ahead and substitute the areas I know. The only one I don't know is the red. So blue is 0.9656, yellow is 0.5832, so the red is 0.3824, which means the probability that the z-score is between 0.21 and 1.82 is 38.24%. So now you've done an in-between probability. Above probabilities are not too hard as long as you remember to subtract. In-betweens, if you're using a table, you have to calculate 2 percentiles and then subtract to find the difference between them. All right, so what percent of Tiger Woods drives are more than 302 yards? So we'll find our z-score again. In this case, 302 minus 304, remember it's the value minus the mean over the standard deviation, negative 0.25, which would be over here. And if I look up negative 2.5 on my 0.25, that would be right here. And so, but that area is for the left area here, 0.4013. So I would have to subtract that from 1, and I would get 0.5987. So 59.87% of drives using the normal model are more than 302 yards. So what percent of Tiger Woods' drives are between 286 and 302 yards? Well, first of all, let's go ahead and put in the z-scores, which we already calculated before. And we know we're looking for the blue area, all right? The yellow area is the 0.0122 that we found earlier. And that is, there you go, that's the yellow area. Then we have 0.4013. That's the from negative 0.25 all the way down. So that's the yellow and the blue area combined. So yellow plus blue has to be 0.4013. So that means I can just substitute in the 0.0122 for the yellow area. So I get the blue area is 0.3891, which means using the normal model for Tiger Woods' drives, approximately 38.91% of drives are between 286 and 302 yards. One more example, we're going to look at the weights of newborn children in the U.S. The mean is 7.5 pounds. They're approximately normally distributed and with a standard deviation of 1.25 pounds. So I'm going to write the normal model. We write it N with the mean, comma, standard deviation. All right, so what's the probability a newborn will weigh between 6 and 7 pounds? So first, let's go ahead and work on the z-score for a 6-pound newborn. That would be z is value minus the mean. So I'm going to go z is 6 minus 7.5 over 1.25, which is negative 1.2. Go ahead and look it up down here and mark it on my curve. And on my table, it is 0.1151. Okay, so if I ask you what percent of babies weigh less than 6 pounds, it would be 11.51% of newborns in the U.S. weigh less than 6 pounds using the normal model. All right, I don't know that exactly that many, but according to the normal model, that's what we predict. All right, now we're going to do what percent of babies weigh less than 7 pounds. So I'm going to do the z-score for that one, which is negative 0.4. And that area is going to be 0.3446. All right, so that's the area there. So how can we determine what percent of babies weigh between 6 and 7 pounds? Well, here's the 6-pound marker, and that's the red area here. And that was 0.1151. Remember, 0.3446 is the whole yellow area. If I'm looking for this blue area right here, that would be, I can say red plus blue is the yellow, right? I know the red is 0.1151. I know the yellow is 0.3446. Solve for blue, and I get 0.2295. So the probability that the z-score is between negative 1.2 and negative 0.4 is 0.2295. The other way I can say the probability the weight is between 6 and 7 pounds is 2.2295. Notice here I use Z for z-scores and X for the actual values in the problem. So if I wanted to write a nice statement in context, I would say using the normal model for weights of newborns, approximately 22.95% of newborns are expected to weigh between 6 and 7 pounds. Be very careful about saying will weigh or things like that because we really don't know.